Tables, rice charts. Rice charts are going to hopefully become your best friend because we use them a lot throughout chemistry. This will be your first segment where we use rice tables. Lots of people call them ice tables. We add the RN, so you have your balanced reaction at the top. The balanced reaction at the top, and then the second row of the table is the initial concentration. The third row of the table is going to be the change in concentration, and then the fourth row is going to be the equilibrium concentration. So, balanced reaction, change in concentration, initial concentration, change in concentration, and then equilibrium concentration. Okay, so your balanced reaction, you're going to write across the top, and then you're going to start building your table. And we're going to insert our values into the table. This is a very good way of keeping track of all your values, making sure that you're going to end up getting the right concentrations to put into your K expression or your law of mass action expression. So let's look here at our first example. See the reaction at the top there. It's going to be the iron 3 plus the thiocyanate giving you this complex ion. It's the iron, ferrous something, thiocyanate. It's a complex ion. We'll talk about those in a little bit. So it tells us that we're going to have 6 molar of the iron and 10 molar of the thiocyanate. And at equilibrium, you're going to end up with this much of the product. So lots of different values. You have initials, you have equilibrium concentration of your product. So what is the value of K? Basically, it wants equilibrium constant. We're going to be solving for that. So we're going to build our chart. We're going to build the rice chart. I'm going to do it down here. So rice, the R, so I write out my reaction here with its correct molar relationship. Reactants on the left, products on the right. So that's my R. Make sure I put that out there so it keeps track of what I'm going to do. Yes? No, not when you're just doing your rice chart. The only time you would really want to pay attention to the phases is if you, like all of these have AQ, so they're all going to be part of equilibrium. The ones that where they have solids or liquids, you can cross them out. Yeah, you would cross out the solids or liquids. Like if this was a liquid, I would just go ahead and do this through that particular part because it doesn't play a role in equilibrium. But this one, all of them are AQ, so they all are going to play a role in finding the equilibrium constant. We will have examples like that where we're going to cross out the solids and liquids and not use them. So then our initial concentration. They gave us the initial concentration of the iron 3. They gave us the initial concentration of the thiocyanate. Now, when they give initial concentrations like that of both reactants, they don't tell you anything about the products. You assume it's 0. So this is 0 molar. Okay? Nothing there. Because they didn't tell us otherwise. So you assume the products are 0. Unless they tell you there's some product there, you're going to assume it's 0. Now the change in concentration. So we're doing change in concentration. The change in concentration, you have to kind of think about it in terms of its molar relationship. This is 1 mole, this is 1 mole, and this is 1 mole, right? So if I lose 1 mole of the iron 3, I'm going to be gaining 1 mole of this compound over here on the right, the product, correct? If I lose the 1 mole of the thiocyanate, the SCN here, I still will be gaining 1 mole of my product. Does everybody see that? So we're going to use X's to represent the amount of moles that would be lost or gained by either side of the reaction. So, since this is 1 mole, it's going to lose a certain amount. And since this is also 1 mole, it's going to also lose that same amount, correct? Because these two things over here have to combine to make one of those things over there. That means if we lose this amount from the iron 3, we lose this amount from our SCN, that means we're going to gain the same amount over on the right-hand side in the product. Does that make sense? So now we know the change in the concentration. And this change is going to be based off of the molar relationships. You can easily look at the coefficients and tell. Now we're going to get our equilibrium concentrations. So this is going to be 6 minus x. This one's going to be 10 minus x. And this one is just going to be x, right? We need to know our K expression. This is Kc or Keq or K. Remember, all of those evolve around concentration. So our product concentration over our reactants concentration. Since they're all 1 molar, that is going to be right there. Okay. Now I can plug in the values. No, this over here is 4. You're right. I'm missing something here because I'm not getting it right. Okay. Yes, you're right. It did tell us the equilibrium concentration of our product. And by telling us the equilibrium concentration of the product, now we can determine what x is. Because if it goes from 0 to 4, guess what x is going to be? X has got to be 4. I'm missing something here. Okay. So that means this is going to be 6 minus the 4, which is going to be 2, right? This is going to be 10 minus the 4, which is going to give me 6. Correct? Yes, so we know all of the equilibrium concentrations. That one, iron 3 is 2 molar. We know that the SCN is 6 molar, and we know that our product is going to be 4 molar. Now we can plug them in to find K. So we're going to have 4 on the top over the 2 times the 6. That's going to give us our K. And you will plug and chug now. And we end up with K being 0.333. So that's the first example of a Rice chart. And they can give you the initials of certain ones and the equilibrium of certain ones so you can determine the x value that changed. So that's one way that they can give you a Rice table type or Rice chart type problem. We're going to show you a few other ways that they can word it and give it to you in different information. So this case, you can calculate the K because you know one of the equilibrium concentrations, you know both, you know some initial concentrations, so you can determine the change. There you go. I wrote it all out, and you set it up, and we end up with our 0.33. All right. Next example here. Same reaction as before. Our initials, though, have changed. We're at the same temperature, too. Why would we need to be at the same temperature? What remains the same at the same temperature? The value of K. So we know our K now. What was our K at this temperature? K is 0.333. So we know the K because we're at the same temperature. That's going to be useful information. Consider the reaction represented by this equation. Initially, we have 10 and 8. We want the equilibrium concentration of the product. So let's go ahead and set up our Rice table again. Initially, I have 10 of my iron. And really, you don't have to write in the molarities and all of that. And once again, we're going to start with 0 here because it tells us we don't have any of that. And because we're still working with the same molar relationship of the reaction, 1 mole of the iron to 1 mole of the thiocyanate is going to make 1 mole of the product. So if I lose from the reactant side, it's going to be the same amount that I'm going to gain over here on the product side. Now this is where I was trying to skip ahead to the harder problems, because we have all of these equilibrium concentrations that all have an X in them. And so when that happens, we know our expression, product over reactants, because we already wrote out that expression, right? So there's our product over reactant. We know our K2, because it's still 0.333. That we know as well. Can we find X now? Yes. Now you have 2 possible ways of finding X. You can multiply it all out and set it to 0 and then use the quadratic formula. Who wants to do that, though? That takes a lot of time, right? So no, we don't want to do that. What else can we do then? We can graph it using the graphing calculator. So let's go ahead and do that instead. Everybody know how to graph these kind of equations in their graphing calculator? If not, I'm going to set up my document camera so you can see it. This is how I plug it in. You might have better ways too, because you guys know the technology probably better than I do. So you need to go, okay, so clear here at the screen. First thing I do is hit my y equals. For those now not having done this in a while in their graphing calculator, y1 is always going to be the k value. So I'm going to plug in the 0.333 there. The k value should be y1. In y2, I'm going to put the rest of the expression. And on top it was x. You can use this button right here as x, or you can do the alpha key and then hit the x down here, which is down here at this button. If you want to do it that way, you can use the alpha if you'd like. So the top is x. I put parentheses around everything just to make sure order of operations stay normal. Hit the divided by. The first one was, what was the first? It was what minus x? 10 minus x. And then the second one was 8 minus x. So I put like the double parentheses to make sure everything stays correct with order of operations. You don't have to, if it does, you know, I don't think you have to do that, but I just do it. Once you get that plugged in, now you can do, and you just hit graph. And you have to wait a moment and let it run the lines. So let it run the lines. Okay? So once you get it graphed, like so, and you might have to set your parameters of your graphing of the y and x axis so that it shows correctly. Then you're going to do the second button, and then you're going to hit the trace button, which is really calc. So that pops up. Second trace, which gives you this, and you're going to press 5 for the intersect. Now it says first curve right here. You're going to see first curve. You have to hit enter through the first curve. It's going to say second curve. You're going to hit enter through the second curve. Guess. You're going to hit enter and it'll give you the intersection. The intersection happens to be this 4.9998 number you see here. So that's virtually what? 5.00. We're going with 5.00 because significant digit-wise it would round up and be 5.00. Correct? So here we end up with x being 5 from the graphing. Remember, we graphed it. So x is 5 now. So can we figure out the equilibrium concentrations? So this is a 5 here. So if we subtract that, at equilibrium, the iron 3 should be a 5 molar. 8 minus 5 gives us 3 molar of that stuff. And here also, since we go from 0 to x, this one's going to be 5 molar. Now we have our equilibrium concentrations. So in this particular case, all it wanted was the product's equilibrium concentration, which ended up being 5 molar. 5 molar. So now what I'd like you to try to do is try to do exercise 7 on your own. You have different initials. We are still at the same temperature, so our K value is still going to be what? 0.333. So we're still at the same temperature. The K value is going to stay at 0.333. Try this one on your own. Set up the rice. When you went ahead and set it up, should have ended up being x over 6 minus x, 6 minus x, right, equals your 0.333. Is that what you plugged into your calculator? Yes? And your intersection should have ended up being 3 molar or 2.998 something. Did you get 2.998 something? Okay. Getting the graphing down so we don't have to use the quadratic. All right. Some generalized information. You don't really need to write this down. Okay. When we're solving equilibrium problems, the rice part, the R, is to write down your balanced equation. You also need to make sure that you put in your initial concentrations, that you can write out your KEQ expression. And you can also calculate Q if that's needed, because sometimes they give you all the initial concentrations, and you can calculate Q if you need to tell which way it's going to proceed to establish equilibrium. Define the change using the X, and the molar relationship. Substitute in the concentrations, and you can calculate K if needed, or you can calculate the missing equilibrium concentrations if needed. So if you want to go back, and you can use these steps later, if you need a refresher while you're doing your problem set tonight or something like that, this is in the PowerPoint. So determine which way the equilibrium reaction will shift. You can either do it by calculating Q, or if you know something starts out with 0, initially, you can pretty much tell that's kind of the common sense way it's talking about. Make a rice chart. Rice charts are always helpful, good visual aids in order to determine and keep your numbers straight. Okay, so finding the equilibrium concentrations for all of these species. Here, we are given all of our our initial concentrations. We're given all the I's here. So we can make a rice chart very simply. Still using that same reaction. We're going to use some new reactions in a minute. But familiarizing ourselves with the way the chart is set up, sometimes it's easier if we just use the same reaction over and over again. So here's our I. Our initial concentrations, 9, 5, and 1. Once again, we're losing 1 mole of our iron, 1 mole of our thiocyanate to make 1 mole of our complex ion over there. And then here, of course, 9 minus x, 5 minus x, and this one's now going to be 1 plus x. We're still sticking with our same temperature. Our KEQ is still 0.333, and all you have to do now is what? Plug it in and graph it. So go ahead and plug it in and graph it. Correct. The only thing that's going to change K is the temperature, because remember, temperature makes the molecules, if you increase temperature, it makes the molecules move faster. So you end up changing your rate, you're changing your amount of collisions, you're going to end up changing your proportion a little bit. But that's the only thing that's going to affect the K value. And do remember here, just like we just talked about a minute ago, that if you come across where there are two intersections on your graph, you always want to make sure you're selecting the one that doesn't come out with a negative concentration. So 5 minus x, this x value has to be, less than 5. If we're looking at this one, the x value has to be less than 5. It can't be more than 5. So you want to make sure that you're choosing, if there are two intersections, you're choosing the one that makes sure all of your concentrations come out positive. Some of them will only have one intersection. Some of the graphs will have two, though. Make sure you choose the one that makes your concentrations all positive, because you can't have a negative concentration. There's no such thing. So what did you guys get when you graphed this one? 3. Get 6 for your iron. You got 3 for your x, right?
Yeah.
So 9 minus 3 should have given you 6 for your equilibrium concentration. So the 9 minus your 3, because if x was 3, 9 minus 6 gives you your, 9 minus the 3 gives you 6. 5 minus the 3 gives you the 2. And 1 plus the 3 should give you this 4 over here. Right? So don't forget to do that little adding at the, or subtracting at the end. You get x is 3, but that's not the concentration. 9 minus the 3 gives you 6, so that's the concentration of iron. 5 minus the 2 gives you that 3 for the concentration of thiocyanate. And then your complex ion over here, 1 plus the 3 gives you 4. All right, different reaction. Yay, finally. Okay, so let's look up here. Couple different things you need to pay attention, because this is where it starts. They change the wording on you. A 2-mole sample of ammonia is introduced into a 1-liter container, or they might say vessel, reaction vessel. That's a big word they use sometimes. At a certain temperature, the ammonia partially dissociates according to the equation. At equilibrium, 1 mole of ammonia remains. Calculate K. So, paying attention up here, looking at some things. Did they give us concentrations to begin with? No. They gave us some moles and they gave us some liters. So what do we have to do? Find the concentrations. No concentrations are given. It's usually pretty easy, though, because it's usually like a 1-liter vessel or a 2-liter vessel. Okay? What's another problem up here that we need to do? What else is wrong that we need to make sure we fix before we begin? Balance the equation. The equation wasn't balanced for us. So we need to put in a 2 here. We need to put in a 3 here. Okay? Those weren't done for us, so we need to keep that in mind. So let's look here. Ammonia, if it's 2 moles in 1 liter, we know the ammonia is going to be 2.0 molar, right? And then it tells us 1 mole of ammonia is left, so 1 mole out of 1 liter. At the end is going to be 1 molar. Okay, so we know those. We're going to put those in our chart correctly. So rice, time for the rice. 2NH3, N2, and 3H2. So, initial concentration was 2 here. What do we assume about the others over here?
0.
Nothing, because they just told us ammonia was introduced into the container. That's it. Now paying attention to our change in concentration. 2 moles of ammonia are going to decompose into 1 mole of nitrogen and 3 moles of our hydrogen. So we're going to lose 2 times the amount from the ammonia, but we are going to gain 1 times the amount in the nitrogen and 3 times the amount for the hydrogen. So every time 2 moles of the ammonia decompose, you're going to get 1 mole of nitrogen, 3 moles of the hydrogen. So, it also told us the equilibrium concentration of the ammonia here, which happened to be 1, because we calculated that from 2 moles divided by the liter. And here, this is going to be X, and this is going to be 3X. Can we determine what X is? Yes. X is, from here to here, the change was 1, so 2x, which was the change, equals 1, right? 2 to 1, that change was 1, but it was 2 times x, so we can figure out x. X happens to be 0.50, correct? So the equilibrium concentration for nitrogen is 0.50. What about for our hydrogen? 1.5, because 3 times 0.5 gives us that value. Okay, now can we calculate K? Yes, so we do need to write out our expression first. We have, what is our product? Concentration of the nitrogen times the concentration of the hydrogen, raised to the 3rd power now. On the bottom, don't forget your ammonia must be raised to the 2nd power. Following our expression. So now we have 0.5 times 1.5 raised to the 3rd power over 1 raised to the 2nd power. So what do we end up with? And we are right, we get our 1.69. Or actually, no, technically, I guess that's not right, because look at our sig figs. We should have considered those two. So really, this should have just been 1.7. 1.7. Go with the least number measured value there. Practice problem. We are going to skip 1 and 2. We're going to do 3 and 4. And then if you want to, you can come back and calculate 1, 2, 5, and 6 on your own and check your answers if you need more practice. But we're going to do 3 and 4 and then move on to the next PowerPoint and review. All right, so here we have a different reaction. We have hydrogen and carbon monoxide going to form methanol. Okay? And they're all gaseous. That's good. We should take a look at their phases to make sure that they're all being incorporated in. Now, 1 liter container holds 1.60 moles of hydrogen. See how we're in liters and moles again, so we need to make sure we calculate our concentrations correctly. Tells us the hydrogen and the carbon monoxide. At this temperature, after equilibrium established, it shows us that we have 0.2 moles of ethanol in the container, so we know the equilibrium concentration, if we calculate that right, of our methanol, and then we can solve for the other components. What is the equilibrium concentration? That's what this EQ here means. Concentration means brackets, so EQ. Equilibrium concentration of our hydrogen and our K. So that's what we're going to do. That means we need to start our rice table. Fun rice tables. Rice chart. So we have 2H2 plus CO giving us methanol. Everything's a gas, so we're going to keep everything in and include it. Now, since everything's out of 1 liter, it's an easy change to change it all to concentrations. So let's go ahead and do that. Hydrogen ends up being 1.06 m, and the carbon monoxide ends up being 1.57 m. So we assume, what about our methanol? Starts out at 0. But we do know something about methanol. Methanol ends up being 0.200 moles at equilibrium, and that's out of 1 liter again, so this one is there. So we know that to begin with. Those are our initial amounts. Now we can insert our changes and go from there. So how much do we lose from the hydrogen? 2x goes away. 2 times x, because there's 2 hydrogens. We're going to lose 1 x out of the carbon monoxide, and we're going to gain x over in the methanol. Because that's a 2 to 1 to 1 relationship. Can I figure out what x is? If I start at 0 here and I end up at 0.2, x has to be what? Okay. Can I figure the other equilibrium concentrations? So this is going to be 1.57 minus 0.200. What does this end up being then? This is going to be 1.37, correct? And this is going to be 2 times, so we need to do 2 times our 0.200 here. So 1.06 minus 2 times 0.200, and that ends up being now we have our equilibrium concentrations, all 3 of them. Those are all our equilibrium concentrations, so we can plug them into the K expression. So we need to write out a K expression. K is going to be the concentration of the methanol over the concentration of the hydrogen squared times the concentration of the carbon monoxide. And once you get really good at equilibrium, you can kind of skip this step of writing out the expression in between when you get faster and better at it. But for right now, make sure that you're writing out the expression and products over reactants, raised to the powers. Make sure you're reviewing those steps. So then, we just plug and chug now. 0.2 on the top over 0.66 squared times 1.37. Correct? And we end up with what? Did you get those answers? Now I'd like you to try number 4 on your own. I'll give you like a couple minutes to set up your table. You pay attention to your container now. How many liters are in the container? 2. So, since there's 2 in the container, you definitely need to be paying attention to calculating your molarities correctly.